Okay, so we'll start now. Can you see my screen or no? Okay. So I'll just quickly do a recap of the main things that we learned about electrons in periodic potentials. And then we actually will look at some of the periodic structures that we encounter most often in nature. So the major points were that the wave functions of the electrons in a periodic potential can be written in this form, where k is an index that comes in from the reciprocal space, and it has this particular form, e to the ik dot r times this part, this sum over reciprocal lattice vectors, which we wrote like this, e to the ik dot r uk. Now uk, as I showed you, because of this particular form, if I translate this by any lattice vector, because g dot e to the I g dot r is 1, I get the same uk. So uk is lattice periodic, but psi k is not. And if you translate psi k, then it will pick up a phase of e to the I k dot capital R. And it is obvious that h cross k is not the momentum of this state. It's not a momentum eigenstate. And k can be confined to the first Brillouin zone. This is fairly simple. So if k is not in the first Brillouin zone, then I can write a k primed, which is in the first Brillouin zone, such that k plus some reciprocal lattice vector g primed is equal to k primed. So now with that definition of k primed, if you write uk primed, you just use this expression, and instead of k, you have k primed. So it is like this. And then because k primed is k plus g primed, I can write this here. And then I define g minus g primed as g double primed. So then g becomes g double prime plus g prime. Remember, g prime is a particular reciprocal lattice vector. So I end up with this form written in terms of k. And this sum over g can be replaced by sum over g prime. So from here, I come here. So I pull out the factor e to the minus ig primed, ck minus g. I change again g prime double prime to g because it's just a dummy index. And so I have this form, so which is exactly uk of r. So therefore, when I write psi k primed r, I have this form, but then k primed was k plus g primed, so it is k plus g primed. So this part was uk. I had this additional factor e to the minus ig primed, which was here. Otherwise, this was uk. So uk primed is this times uk. So this e to the ig primed r will cancel this factor, and I'll get psi of k. So this is again explicitly showing that this wave function is periodic in the reciprocal space. And then I left the algebra part for you to figure out that if I take the full Hamiltonian of the electron in the periodic potential, apply it on this electronic wave function, then I'll end up getting this kind of an equation for uk. So this eigenvalue equation for uk. Remember, this was equal to epsilon psi k of r. So it's the same eigenvalue. But the operator here is not exactly h, but something else. But the main argument here was that this is still a Hermitian operator. So I have an eigenvalue equation for a Hermitian operator, which is a Hermitian operator on the wave function with the boundary condition that it is periodic. is lattice period. So therefore, on very general grounds, I expect to get an infinite set of solutions with discrete eigenvalues, and those eigenvalues we called, we denoted by this index n. And then we argued that we expect epsilon n k to be a continuous function of k, which is just a parameter. And these continuous functions, if we label them in such a way that when I change k by a reciprocal lattice vector, I end up getting the same eigenvalue, then this energy eigenvalues corresponding to a particular n constitute a band. So as we go along, I mean, I showed you some pictures of energy bands, and as we go along, we'll see more of those. So these were the main concepts for electrons in a periodic potential. So now we'll look at some of the lattice structures that we encounter, and it's important that some basic lattice structures you should be familiar with. So how do we sort of designate lattice? I mean, how do we name them? What are they, and so on? So that's what we are trying to look at right now. So what are and these are of course determined by the symmetries of the lattice that we have. So what are the symmetries that we have in a lattice? There are two types of symmetries in a lattice. One is that we use to define a lattice, which is
Hello, sir.
yes.
Can you tap the screen?
Can you see it? It's somehow getting darker.
So I think you should click on the lower side of the screen. Yeah, now it's fine.
Is it okay? All right. So translation by any lattice vector, that's the symmetry. I mean, that's how we define a lattice. And there can be other types of symmetry, which is operations that leave a lattice point. Could be, I mean, the right statement would be at least one lattice point unchanged. Could be more than one. So these are, of course, so the point is that under these operations, the lattice is mapped onto itself. So the new position of the lattice, the new lattice and the old lattice are exactly the same. So that is what we call a symmetry operation. So these are translational symmetry. And these are called, I'll come to the nomenclature later. But let me first give examples, then it will become clearer. So this is obvious because if you translate the lattice by any vector which is a linear, integer linear combination of of our lattice vectors, then it will get mapped onto itself. As an example of this, suppose you take a cubic lattice. Let me give you the simplest example. You take a cubic lattice and you consider a line which is running along, let's say, z direction along, through the points. Okay. So let me take this example. Okay, am I visible? Okay, here. So this is a cube, and I consider a line which is going like this, an axis goes through these points. There are an infinite number of lattice points along this line, and there are cubes all around it. So it's a cubic lattice. And then if I rotate this by 90 degrees around this axis, the lattice gets mapped onto itself. So that's an example of this kind of an operation. If I sort of invert the lattice about any point, say I have a lattice point here at the corner of the cube, and I invert the lattice with respect to this point, then the lattice gets mapped onto itself. So that's another symmetry operation. The first one is a rotational symmetry. The second one is inversion symmetry. I can also consider reflections in planes. For example, if I suppose this is a one cube of the cubic lattice that I have, and I consider this plane. This is one of the lattice planes that we talked about earlier. And if I reflect the lattice about this plane, it just gets mapped onto itself. So that's another symmetry operation of the lattice, the reflection in a plane. So these are symmetry operations, but each one of the last three, that is rotation, inversion, reflection in a plane, all of these symmetry operations leave at least one point unchanged. In case of inversion, it's one point that remains unchanged. In case of reflection in a plane, all the points in the plane remain unchanged. When you rotate, it's the points along the axis that remain unchanged. So at least one point remains unchanged. Now, talking to the MSc students, probably you have not got into group theory in your Math Methods 2 course yet, but that's one of the major parts of that course. So basically, these symmetry operations form groups, and symmetry operations that leave one point unchanged constitute what are called point groups. And so these operations are point group symmetry operations, whereas this constitute a sort of continuous symmetry, or at least discrete continuous symmetry. So they form, so these things taken together form what is called the space group of symmetry of the lattice. So I'll not get into any more sort of mathematical discussion of this, but just to give you the nomenclature. So these set of operations gives you the point group symmetry of the lattice, and this taken together gives you what is called the space group symmetry of the lattice. And I won't even get into the space group classification of the lattice, but with this point group operations, at least intuitively, geometrically, it's not difficult to visualize them. So I'll talk about this a little bit, and based on this, you can classify lattices into basically 7 types. So that is what I want to talk about now.
Sir?
Yes.
Sir, rotation falls in space group symmetry, right?
No. This is a discrete rotation. If it's a continuous rotation, then yes, but this is a discrete rotation. If I have a cubic lattice, then only under rotations by 90 degrees, I'll have the lattice unchanged. Any arbitrary rotation is not going to leave it unchanged.
Okay.
When I say 90 degrees, it's 90 degrees about one of the axes running along X, Y, or Z. If I choose it, there are other axes around which a rotation by a different angle will leave the lattice unchanged. So it depends on which axis of rotation you are talking about. If you take a body diagonal, then it's a different angle. But my point is that it's only under rotations by some specific angles that leaves the lattice unchanged. So this is a point group symmetry.
Okay. Okay, sir.
Mm-hmm. All right. So the simplest lattice structure, of course, is the cubic lattice structure. It's as I showed you, this is one of the cubes. Then you put cubes on all sides and continue indefinitely, and the points at the corners of the cubes form the cubic lattice. And so if you have lattice points only at the corners of the cubes, you call that a simple cubic lattice. So the first lattice that you need to be familiar with is the cubic lattice. But then there are three different cubic lattice types. There are three different cubic lattice types. One is simple cubic. Then you have face-centered cubic, and the other is body-centered cubic. I'll come to more of this later. These are the very common lattice structures. I mean, many elemental solids, for example, get into these structures. Rarely simple cubic. I mean, in fact, of the lighter atoms, lighter elements, none of these form simple cubic structures. Mostly they form face-centered and body-centered cubic structures. Now, okay, so cube is very easy to understand. Now, suppose I take this cubic crystal, cubic lattice, and I stretch it along. Let's say this is my Z direction, and I stretch the cube, that is all the cubes, along this direction, so that if I call the lengths of the lattice constants excuse me, as A along X, B along Y, and C along Z, then in a cubic lattice, A is equal to B is equal to C. But then now I stretch it along the Z direction so that C becomes different from A and B. So in this, the standard notation is A is equal to B. And all angles between any pair of lattice vectors is 90 degrees. So they are designated by alpha, beta, gamma usually. Now, if I make C different from A and B, what I get is turns out that if you stretch either body-centered cubic or face-centered cubic, you end up getting similar, both of these would fall in the same category of center tetragonal, but I'll not get into such details. So just remember that if you stretch a cube along one of the directions so that A is equal to B, but these are not equal to C, then you get a tetragonal lattice. Okay. So as you understand, what we are doing is we started with a high symmetry structure, and then we are gradually reducing the symmetry. So now in the tetragonal lattice, what we can do is we can now make A and B different. Okay. So so earlier I stretched it along C. Now suppose I make A and B different. So stretch it along another direction. A and B are different. So then that will give me what is called an orthorhombic lattice, and there are 4 types of orthorhombic lattice, and I'll not get into the details of those. You can get the names in the textbooks if you want, but basically here the point is A is not equal to B is equal to C. So they are all different. Okay. So now we have a crystal in which we have a lattice in which the lattice vectors are still mutually perpendicular, but their lengths are not the same. 3 of them have different lengths. A, B, and C are different. Now what I do is, suppose this is C axis, I distort. So I still have a square face perpendicular to each of these axes. Now, if I distort, suppose I distort this square face. I'm sorry, it's not a square face, it's a rectangular face because A is different from B. So now I distort this rectangular face into some general, parallelogram. So if I give it that distortion, I get what is called the monoclinic lattice. And you will find there are 2 types of monoclinic lattices.
Sir?
Mm-hmm.
Sir, is there any way to find out how many types of cubic or tetragonal or these things are there? Like you said cubic, there are 3 types, tetragonal 2 types. So how do we know that there aren't any other?
We don't see any other. So when I say there are 3 types of cubic lattices, what I mean is, this statement is about our experience of nature, not a mathematical statement. Okay, maybe I'll explain when I show you the actual structures. Okay, so we have made A, B, and C different. We have distorted the face perpendicular to the C axis. And as the next step, we make C not perpendicular to A and B. Okay, so C axis was still perpendicular to A and B axis. Now suppose I tilt it. So I tilt this whole C axis so that it is no longer perpendicular to A and B. Then what you will have is what is called a triclinic lattice. Okay. Sixth. So how do we start? Why did I start? We started from a cubic structure and then made A, B, and C different, then distorted one of the faces, then tilted the C axis. But the stretching started along the 3 lattice directions. That is, for a cubic system along X, Y, and Z axis. But suppose I had distorted the cubic structure along its body diagonal to start with. Then I would have got what is called a trigonal lattice. And there is only one type of trigonal lattice. And finally, another thing that is very important is what is called a hexagonal lattice. Obvious, right? What it means, you have hexagons in a plane, and then these hexagons are stacked in some way. Now, the stacking is very important. I'll come to stacking later, but this is the seventh and the last type of lattice structure. So you only have these 7 types of lattice structures. For example, so obviously hexagonal lattices would have 6-fold rotational symmetry in an axis perpendicular to the hexagon. Note that you cannot have, for example, lattices with 5-fold rotational symmetry axis. That's not sort of compatible with symmetry of space. So in other words, you cannot have regular pentagons tiling a plane. So therefore, you cannot have lattices that have 5-fold rotational symmetry. So these are the possible symmetry structures. And with that, so most important ones that you should remember are these ones. They are encountered most often. And yeah. Okay. So with those, with that classification, what I'll now do is I'll show you some pictures and show you how the primitive lattice vectors are written and how some of the commonly encountered solids crystallize into these structures. Okay. So I'll stop this and okay, so I have talked about this before also, but let me show you once again. So this is the example of a Bcc lattice, as you can see. The blue atoms are at the corners of the cube, if you want, and the green atoms or the green points are at the body centers. How have this? No, I'm sorry, that's not how they have this. So this green one, can you see my pointer?
Yes, sir.
Okay, so this is at the origin, let us say. So these blue points are at the corners of a cube, and these green points, these 3, are at the body centers. And the primitive lattice vectors are generally taken to be these vectors. So in our language, this would be A1, A2, and A3 along these body diagonals. The conventional unit cell would be a cube, which is, let's say, this cube, or whichever cube you wish to take. And then if you take a conventional cell, cubic cell, then you have to have a 2-atom basis to describe the lattice. One at the origin, 0, 0, 0, and the other at the body center at A by 2, A by 2, A by 2, where A is the side of a cube. So that's how you can visualize a body-centered cubic structure. So the expressions for these lattice vectors, etc., are given in any textbook, definitely in Ashcroft and Marvin. So that is something you should, I mean, you should know this. The primitive lattice vectors of a Bcc lattice, the primitive lattice vectors of an Fcc lattice. From that, you should be able to calculate the primitive vectors of the corresponding reciprocal lattices. Okay, so that's Bcc. This is Fcc. So you have cubes and all the faces of the cube has they have points at the face center. So this is and you repeat this, so you have Fcc lattice. Now, one thing I want to sort of point out here is that the way I sort of described and the way these lattice vectors are drawn here, it may seem that these two sets of points, the ones at the corners and at the body centers, are not equivalent. That is not true. All points are equivalent here, in the sense that I could think of these points, which are now at the body centers, to form the cubic structure, to be at the corners of the cube. And then if I do that, then these points would be the points at the body center. So basically, if I, the skeleton of the cubes that I have, if I translate this whole thing by a by 4, a by 4, a by 4, then these points would now fall at the cubic, the corners of the cube, and these points would become the body centers. So all the points are equivalent. So this is a Bravais lattice. Similarly, the Fcc lattice is also a Bravais lattice. Yeah. All right. What do I have next? Okay, HCP structure. So hexagonal lattice, there is only one type of hexagonal lattice, but then the most elemental solids we encounter in the hexagonal structure are not simple hexagonal structures. These are called they form what are called hexagonal closed packed structures. So how do you understand hexagonal closed packed structures? You have a hexagon here. So for example, suppose this is my C axis. And I have, so these are lattice planes perpendicular to the C axis. So these green planes are lattice planes perpendicular to the C axis. So in one plane, you have these hexagons, or centered hexagons, if you wish. And this plane is exactly the same as that plane. So the two green planes here are identical. But then you have one plane in between. In this second plane, so you see you have 6 triangles here. Now, 3 of those triangles, centers of 3 of those triangles have atoms above them. So in this middle plane, there are 3 atoms in this part of the lattice, and these points are directly above the center of this triangle. This point is directly above the center of this triangle, and so on. So out of these 6 triangles, 3 of them have atoms above them. But so basically, this plane, when you sort of repeat it in this plane, you will again have a hexagonal lattice exactly like this, but it is displaced by this amount in the XY plane. So this is what is called a hexagonal closed packed lattice. And this particular stacking that I was talking about, so this stacking, so you see, suppose this plane I called my A plane. This plane I call B plane. I call it B because the arrangement of atoms is different. In-plane arrangement of atoms is different in this red plane compared to this green plane. So if this is A, I call this B, but then this one is again A, because on this, the atoms are exactly at the same locations as the A plane. So the stacking here is AB, 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 and so on. So the stacking of atoms you have in a hexagonal closed packed lattice perpendicular to the C axis is AB, AB. On the other hand, if you just, okay, now suppose in the third plane, instead of having atoms exactly above the atoms in the first plane, I had put atoms above the centers of the other 3 triangles here, okay? Then that plane would have been different from the first plane and would have been different from the second plane, but it would still have been a hexagonal sort of lattice. So then the stacking would have become A, B, C, and the fourth plane could have been the same as the first plane. So then the stacking would have been ABC, ABC, ABC. This ABC stacking is just the 111 planes of the Fcc lattice. So there's a very close connection between the Fcc lattice and HCP lattice. In HCP lattice, you have AB stacking of atoms perpendicular to the C axis. In Fcc lattice, you have ABC stacking of the atoms perpendicular to the 111 direction. Okay, so that is about crystal structures. Stop this. Let us now look at some structures that commonly encountered metals form. I'll just show you the tables from the textbook. So some things you should be familiar with. See this table 4.1 in Ashcroft's book. So these are the list of elements which form face-centered cubic crystal structure. So for example, most metals actually, many metals you will find, for example, you see silver, aluminum, gold, calcium, copper, nickel, lead, palladium, platinum, rhodium, etc. They form face-centered cubic structure. Similarly, there is a fairly large number of elements that form BCC structure. Iron is one of them, and usually the alkali elements form BCC structure: potassium, lithium, sodium, rubidium, and so on. And then there are some elements that form hexagonal closed pack structures. So let us see. Yeah, these are the ones. So there's a large number of them that form hexagonal closed pack structures, and cobalt is one, among the most commonly encountered metals. Cobalt forms HCP structure. Magnesium is another. Now, apart from this so these are monatomic, solids. You could have compounds, and they also crystallize in these kind of Fcc or Bcc structures. And the most common ones are, let me just try to dig out something. So if you look at this structure, it's a cubic system, as you can see. These red atoms form an Fcc lattice. So these are the corners of the cube, and these are the face centers. So 8 corners and 6 faces, 1, 2, 3, 4, 5, and 6. So that's an Fcc lattice. These blue atoms, although it's this picture shows only a single cube, but if you sort of repeat it, you will find that the blue points also form an Fcc lattice. But this Fcc lattice is translated with respect to this Fcc lattice, the red one, by a by 4, a by 4, a by 4. So if this is my origin, the coordinate of this point is a by 4, a by 4, a by 4. So now it is easy to visualize, right? You have one Fcc lattice shown by the red points, and then interpenetrating another Fcc lattice shown by the blue points, where this atom is shifted by a by 4, a by 4, a by 4. So this is a very common structure, and this structure, if both red and blue atoms are of the same type, then this is called a diamond structure. It's called a diamond structure because diamond forms this structure. Simple. If all the atoms are carbon atoms, you have diamond. In fact, silicon and germanium, they also form this structure. If the two atoms are different, you call this a zinc blende structure, ZNS. So in a zinc blende structure, this could be zinc, this could be sulfur. Or boron nitride also forms this structure. So this could be, whatever, boron or nitrogen, this could be the other one. So that's called a zinc blende structure. If all the atoms are the same, you call that a diamond structure. And as I said, diamond, silicon, germanium, they form this structure. Another very common type of crystal structure that you encounter for compounds is what is called NaCl structure. Let's see if I have it. Yes. So one set of atoms is sodium, the other set is chlorine. Again, you see it has a cubic structure. But then, how do you define your lattice? So, as you can see, the blue atoms form an Fcc lattice. The red ones also form an Fcc lattice. So, in order to define this crystal structure, you have to take an Fcc lattice with a 2-atom basis. So if I take an Fcc lattice with this much as my cubic lattice constant, and take, for example, these 2 atoms as my basis, then I can describe this crystal structure. So it's an Fcc lattice. It's an Fcc lattice with a 2-atom basis, 1 chlorine and 1 sodium. Cesium chloride forms similarly interpenetrating Bcc structure. Okay, so that is something you can look up. So now, so this is sort of to give you some examples and some sense of how actual elements and compounds form crystal structure and how these sort of cubic, etc. Symmetries. I showed you only cubic and hexagonal structures, not tetragonal or orthorhombic. But when you go to other compounds, you have tetragonal and orthorhombic sort of structures. So let's not get into that. Okay, so do you have any questions at this point?
Sir, here NaCl, in the case of NaCl or ZNS, we can replace. Can we replace the Nas with Cls, and we get the same thing?
Na with what?
Na with chlorine and sodium, and chlorine with sodium, we get the same.
Oh yeah, absolutely. See this designation of red and blue is completely arbitrary.
Yeah, but if we have something like calcium chloride, then calcium should be 2. No, calcium should be 1, and chlorine should be 2.
Okay. Firstly, it's CaCl2, right? So it cannot have a 2-atom basis anyway. It has to have 3. Right?
Okay. So
by
then,
replacing, yes, go ahead.
I mean, okay,
So I don't often know what exactly the crystal structure is. Calcium chloride, obviously, it's some sort of cubic structure. It looks like it's a body-centered cubic structure. And so you would have to have perhaps these two, I don't know, I have to see which ones are chlorine. So probably if you have these two chlorine atoms, these two calcium atoms, then corresponding to those, you have to have how many? 4 chlorine atoms, right? CaCl2. So why don't you just look it up? So my point is that it cannot have 2 atoms in the basis. So simply replacing sodium by calcium, you will not get a CaCl2 structure. It will be something different. You have to respect the stoichiometry. Right? Is that clear?
yes, sir.
You have the advantage of looking up, searching things up on Google and looking at pictures. We didn't have such colorful pictures available in our times. Okay. There's one more point that I wanted to do. So, now that we understand these structures, let us go back to something we talked about while discussing the scattering experiments and see how these things show up. Just give me a minute. So we had found this expression for the structure factor. And what we had argued is that if I have now, instead of just a single atom, I have more than one atoms in my unit cell, then my Ng would be like this. So this is what I had shown you earlier. Now, so this has consequences. Okay. So suppose you are doing a scattering experiment on a BCC, elemental BCC solid. And typically this BCC solid, I mean, these lattice planes and so on are designated according to the conventional unit cell. So if I use the conventional unit cell, then the Bcc lattice consists of a 2-atom basis. So there are 2 atoms in a unit cell, one at 0, 0, 0, the other at A by 2, A by 2, A by 2. Okay, and let me now look up that expression. Okay, now, so what will this object be? I think I had termed this as the geometrical structure factor, but whatever. So, so one of the D's is 0. So I had called it, I think, S of G. So S of G is 1 plus and G is generally of the form. Okay, now here is something I forgot to sort of discuss, is that, I mean, I had written the definitions earlier. So if I have the 3 lattice vectors, A1, A2, and A3, from these I can define the lattice vectors for the reciprocal space and so on. There is a 2 pi factor. And so on, B2 and B3. So this is something you should work out. For example, if you, what you should sort of very well understand and work out is that if you have a simple cubic lattice, you take the 3 lattice vectors corresponding to the simple cubic lattice, you calculate what are these, you will find that, so these vectors B1, B2, B3 will tell you what sort of a reciprocal lattice you have corresponding to this direct space lattice. So if you have a simple cubic lattice in the direct space, you have a simple cubic lattice in the reciprocal space. If you have Fcc here, you will have Bcc here. If you have Bcc here, you will have Fcc here. These are things you should, always remember. And if you work it, I mean, you should definitely work this out. Pretty straightforward. And once you work it out, you should remember it, always. All right. And so if A1, if I'm in a simple cubic lattice, then A1 is simply A times X cap. And you can figure out that B1 will be, by this prescription, B1 will be twice pi over A X cap. And B2 will be twice pi over A Y cap. B3. So these are the 3 vectors of the primitive vectors of the reciprocal lattice corresponding to a simple cubic lattice. Okay. So then this will be So this is a general G for the simple cubic lattice, because G's are integer combinations of B1, B2, and B3. So that's a G times, and D is this vector. So A by 2 dot product. Okay, so this is 1 plus minus 1 to the power n1 plus n2 plus n3. So its value depends on what this combination n1, n2, and n3 are. So if n1 plus n2 plus n3 happen to be even, then this is 2 and 0 is into 3. So therefore, even though you would expect to see this Bragg peaks at certain G vectors, but because of this particular combination of n1, n2, and n3, you won't find anything there. So these actually show up, when one does scattering experiments. And depending on whether you are viewing the Bcc lattice in terms of its reciprocal lattice vectors, the primitive lattice vectors, which are pointing along the body diagonals, or in terms of its conventional cubic lattice vectors like here, your interpretation of the results have to be done accordingly. So there is a section, small discussion in Ashroff's book on this. So you should read up that part. Just to show that this geometric structure factor does have consequences when you do experiments, and you have to keep that in mind. Okay, so I think I'll end the discussion on lattice structures here, and now we'll move on to something totally different. Not related to lattice structures per se, but studying electronic structure of, in periodic potentials once again. So if you have any questions at this point, you can ask. Well, if not, then let's move on. So before I write any equation on the board, so let me give you a very clear idea of what we are trying to do here. We have free electrons. We have studied the Sommerfeld model. We have free electrons. So that's sort of the starting point that we have. And then what we are trying to do here is that if the free electrons experience weak periodic potential because of the lattice structure, how do the electronic energy levels and wave functions change? So that is what one is trying to do here. So the starting point, so in a way, we are looking at this weak periodic potential as a perturbation on the free electron energy levels and asking the question, how are they affected? How much do the sort of electronic energies and wave functions change because of this weak periodic potential? Now, obviously, this approach is going to be more useful where the electrons are really free electrons. And for that, as we saw, metals are the best sort of situations where you can apply this approach. But even with this, we learn a lot of things that sort of seemed problematic when we were doing the, for example, Drude theory. So we'll come to that as we go along. So let us start with what we have already learned about the structure of wave functions of electrons in a periodic potential. So we saw that we could write, I mean, this was our starting point. So phi of r is so this is the electronic wave function in a periodic potential, where these are the coefficients, and then these states have some energy epsilon. So if I apply the Hamiltonian, I mean the eigenvalue equation can be written in the following way. I think we had written this earlier also. So this is the equation that we will use. Now for a given k here, there are an infinite number of ck minus g. There are an infinite number of solutions. And now we can view those infinite number of solutions as our bands. So for example, if I write this equation for a particular g, let's say g naught, okay, I'll have this crossover twice. So let's, can you hear me?
Yes.
Okay. How do I use the notation? Okay. So let me call these objects. These are the free electron energies. So I'll call these epsilon naught k minus g. Okay. So I'm writing this equation for a particular g naught. So I'll have this. Plus sum over all g's this thing. And so I'll have There'll be a G naught minus G naught term. I'm not writing this, and I'll tell you why I'm not writing this. The next term will be G1 minus G naught. And so on. That is the equation. I can write a similar equation for G1, for example. Then I'll have here G naught minus G1 and here I'll have epsilon naught A minus G1 and so on. So these are the equations that I have. Now, why am I not writing the sort of U0 terms? What is U0? The way we had defined the Fourier transforms over a unit pair. G is 0 here, so e to the ig dot r is 1. So this is just the average of the potential that electron experiences within a unit cell. It's a constant, some constant for a given crystal. So I can always redefine my energies so that this is now 0. So I define that to be 0. So with that definition, I have just dropped all the U0 terms. So these are the sort of set of equations that you have. And for each k, you have these coefficients Ck minus G, Ck minus G1, Ck minus G2, and so on, and the corresponding energies, for K minus G, K minus G1, and so on. Okay. So now let us see what happens. So as I said, the way we are sort of visualizing this is that we are, so we start with the free electron picture, and then these electrons experience a periodic potential due to the crystal. If the potential was exactly 0, so if U was 0, what would we get? So all U's were 0. So if I focus on this equation, all U's are 0. So all these terms would just go away, and I'll have so then either this has to be 0 or that has to be 0. There should be a G0. Okay. Right. Now, suppose there are no degeneracies in the sense that for a given K, this the energy of K minus G state is not equal to energy of any other K minus G prime state. So there are no such degeneracies. Now, if there are no such degeneracies, then only for this, I'll have this term equal to 0. Only for a particular G, I'll have this thing equal to 0. So in that case, epsilon would simply be epsilon naught K minus G. And I'll get a solution which is of this form. And if G happens to be 0, then I get the familiar e to the ik dot r solution. That's the free particle solution that I have. Now, what happens if I have such degeneracies? If there are more than one G's for which energies of K minus G states are equal. So in that case, there are more terms like this where this is 0. Now, for a, for such, so if I have degenerate solutions, then any linear combination of those degenerate solutions would still be a solution of this equation. So in that case, I can choose whatever Ck minus Gi's that I wish. So if I have a set of G's, let me write it here. I'll erase this. So this was this discussion was when there was no degeneracy. Now, if I have G1, G2, etc., up to some Gn, where epsilon they are degenerate. Now, if that happens, then so I can choose the corresponding Ck minus Gi's, whatever I want, because linear combination of degenerate solutions still remain a solution of the equation. So these are simple ideas, but these ideas will be used in the subsequent discussion. So this was in the case when there is degeneracy. I'm sorry, when U is exactly 0. But in a real solid, of course, U is not exactly 0. However, we treat U as a weak potential. So U is sort of the perturbation on the free particle solutions. And we now want to check its effect on these free electron states. So what we really mean when we talk about degeneracy is not that these energies have to be exactly equal, but the question is whether these energies are equal within U. So case 1, the earlier case was that there is no degeneracy. Now here, what we really mean is, so now we have U not 0, but small. And the first case that we want to discuss is some so what we mean when I say there is no degeneracy is this is greater than U small not G1. So then using this equation, what I'll have is we take summation G not equal to G1 because of that condition that we have chosen U0 equal to 0. So this is the equation we get for Ck minus G1 and epsilon, corresponding epsilon when U is non-zero. However, there is no degeneracy within an energy scale of U, which is a small scale here. And now the argument is that, next step of the argument is that, so we are trying to find the solution for K minus G1. And in case of this, no degeneracy, all other Ck minus G are small. And we'll see what they are. So we'll just again we can take this equation and write an expression for Ck minus G for one of the G's which is not equal to G1. So for some G which is not G1, we can write Ck minus G as okay. So now let us see what we get from what we can argue from here. So we have a situation where we are looking at epsilon K minus G. So Ck minus G1, this energy, the free electron energy at K minus G1 is not degenerate with any other K minus G. So the solution that we have there, the C is something which is not small, okay? Let's say something of order 1. So Ck minus G1 is something that is order 1. And remember, U is a small quantity. So the last expression that I have written there, that's an expression for some other G, which is not equal to G1. So that's the Ck minus G. Now there are two terms. The first term comes from Ck minus G1. And because of this lack of degeneracy, I'm looking at a G which is not G1. So these two energies are not close. So therefore, so this epsilon is something that is like, this will give me a solution for K minus G1. So this is large compared to a scale of U. So the denominator in the first term or in the second term is something that is large compared to the scale of U. And therefore, it will not cancel the U in the numerator. In other words, that U remains in the numerator. Now, Ck minus G1 is not a small quantity. So therefore, the first term will be as it is. I mean, there is no cancellation and so on. That's the leading term. But the second term, again, the denominator is something that is large compared to the scale of U. And we expect Ck minus G primes to be, those are small quantities. So therefore, the second term will be of the order of u squared. So we have the first term plus something that's of the order of u squared. So that's the argument from here. And so then what we do is you take this expression for Ck minus G, one of these Ck minus G's, which is when G is not G1, and plug this in here. Okay. So the first term will give you a contribution which will be order u squared times Ck minus sorry. So you will get an order u times Ck minus G1, this was, and the second term here, I'm sorry, I'm just confusing. So this was my second term, and the second term I had, so this should be G prime. Sorry, what I meant was this is G1 minus G, Ck minus. So when I take this and plug this in here, so this with this will give me something that is u squared. But this is already u squared and there is a u here. So this will give me something which is u cubed. So when I plug this in here, this expression for Ck minus G, I'll have G minus G1, G1 minus G. So you have u mod G1 minus squared. And that is it. And there was a Ck minus G1 here. So that's what you will get. Sorry, the board space is turning out to be a little small for my comfort, but nevertheless, so this is plus something which is order u cubed. So the point was that in the case when u was 0, this thing was exactly equal to 0. But now that we have taken u to be non-zero but small, we get something which is order u squared to the leading order. So in other words, the change in free electron energies in situations where there are no degeneracies, the change from the free electron energy is of the order of u squared. But then what happens when you have such degeneracies or near degeneracies? So we have some epsilon. So these energies are now within a scale of u of each other. So then I can write equations for one of these as so I is now one of these 1, 2, 3 up to n. And when I write this, I'll separate out two types of terms. One type of terms which will contain one of these indices, and the other terms which will not contain one of these indices. So the point is, again, let me repeat that these energies are now within u of each other, but all other energies are well separated from these energies in the scale of u. So in that case, I'm writing this equation for one of these GI, K minus GI. And from there, we can write, okay, so that's one equation. The other is, what do we get for the coefficients of G's that are not part of this? So this would be G. Okay, so this is for G's which will not give one of the near degenerate solutions, and this is for a GI which is one of those near degenerate solutions. So as in the previous case, we'll have, so you can just, check what are the orders of these things. So these CKs are not small, these CKs are small, so that the second term would be something of the order U squared. The first term would be important. So this could be written as 1 minus epsilon. And GJ. And then I can plug this thing into there, and some terms will be order U cubed, so I can neglect that. So basically, then what I'm focusing on, let's say I write the leading order term. So then leading order term would be, so if I plug this CK minus G into this, okay, so this is plugged into that. So then I'll get the leading order term in this sort of equation is so basically we'll get some leading term plus some u squared term plus some u cube term. So I'm keeping only the leading order term. The leading order term will involve only those GI that are part of these near degenerate solutions. So basically, we have these equations within this degenerate sort of set. Okay, so we have got this equation. Now the question is, what is the sort of importance of this one? What do we learn from this? I think the best way to sort of appreciate what we learned from this is to take a simple case where there is only a two-fold degeneracy. So let me just repeat once more what we have done here. So we have now considered a case where there are several G's such that these free electron energies for some K, this K minus G1 epsilon or K minus G2, etc., are within U of each other, but all other K minus G's are far from these on a scale of U. So using the general equation that we wrote, we can write this thing for one of these GIs to be, I have separated out two kinds of terms, one in which I have GJs belonging to this set, the other which does not contain one of these near degenerate G's. Okay. By using arguments exactly as before, I mean, on physical grounds also, I expect this to be small. So I can explicitly write this as like in this, and as in the argument before. Earlier, we had one leading term and then terms of order U squared. Now we have several leading order terms plus something of order U squared. Now this Ck minus G is plugged back into this, and then I can write this equation in this form. Now, when you plug this into this, you will get some leading term, which is basically this, which involves GJs that belong to this set. Then you will have some term which is order U squared, and then you will have some further terms which is of the order U cubed. So all those U squared and U cubed terms have been left out, and I'm just writing the leading order terms on the right hand side. So basically that will involve only these things, these G's. Okay. Now the question is, what is the meaning of all this? So I'll start the discussion today and maybe we'll complete it next time. So as I said, suppose we consider the case two near degenerate levels, and so then I explicitly write the equations for these two. So the last equation that I wrote just now, so I'm writing these equations explicitly for the two G's, G1 and G2. Right. Let's just do some simple change of notation. With that, this will become okay. So these are the equations I have, and this is just this. So what is the degeneracy we are talking about? We are talking about a degeneracy, which means this is close to this. These are free particle energies, remember. So this goes as h cross squared q squared r to n, and similarly h cross squared. So this would imply that mod of q is g. Now, in order to appreciate what this means, we have to have some idea about the reciprocal space and what are called Bragg planes. Now, here I need to go back to our discussion on scattering experiments. So if you check your notes, what we had got was that, okay, maybe I don't need to bring up that expression, but let me tell you what these Bragg planes are, and then we can proceed from here. So just a while before, we were discussing the reciprocal lattices corresponding to simple cubic or Fcc and Bcc and so on. So let us consider a simple cubic lattice for ease of understanding. So the simple cubic lattice vectors in the real space are A1 is this, and A2 and A3 are along Y and Z. And the corresponding B's are along Y and Z. The Brillouin zone of a reciprocal, the Brillouin zone of a particular lattice is the Wegener side cell reciprocal lattice. Can you hear me?
Yes, sir.
My mic switched off. Am I audible?
Yes. Yeah.
Yes.
Can you all hear me?
Yes, sir. We can hear you.
Okay. My microphone switched off. Anyway, now if you can hear me, that's okay. Now, so all right. So what we discussed was that the Wigner side cell in the reciprocal lattice is the first nozzle. So let us consider one of these, this cubic lattice, and then this vector. I'm just drawing it along the x direction. I'm not trying to draw a cube. So this is the reciprocal space, this is 0, and this is, let's say, the B1 vector. And if this is B1, this will be the 2B1 vector, and so on. So these are my reciprocal. Similarly, on this side, I'll have minus B1 and minus 2B1 and so on. So these are the reciprocal lattice vectors. So if I consider this, for example, and I draw a line here, or plane here, in 3D. So if I draw a plane perpendicular to this vector exactly halfway, this vector is obviously B1 by 2. So these planes are called Bragg planes. So that's what we are referring to. Okay. Maybe I'll explain again why these are called Bragg planes, but let us go ahead with this for now. So, so these planes, which are sort of dividing reciprocal lattice vectors into half, are called Bragg planes. So this is possible only when Q is close to a Bragg plane. So let me try to draw a diagram if I can. Here is my origin. This is, in this case, this is the G vector. So this line cuts this. So this is the origin of reciprocal space. This is G. This cuts, plane cuts this into half. So this vector, this much is G by 2. And not a very good drawing, but nevertheless. So let's say this is my Q. And this is G. So Q will be equal to Q minus G when Q is exactly on this plane. And if it's close to the plane, then this is approximately satisfied. So therefore, these conditions are satisfied, these degeneracies are satisfied only when Q's are close to the Bragg planes. By Bragg planes, we mean planes that cut reciprocal lattice vectors into half. All right. Let me finish this part, then we'll stop today. Okay, so now suppose that we have a Q which is on the Bragg plane or close to the Bragg plane. Then what do we get? We have these two equations and with this condition. So these two equations, if I write these as equations for CQ and CKQ minus G with the corresponding coefficients, this will have, or these two will have solutions when the determinant of the coefficients is 0, which will give me a condition that x
So when this condition is satisfied, I'll have solutions for non-trivial solutions for Ck and Ck minus G. So, and then, okay, so from here, what I can do is I can find the value of epsilon. So the epsilon I'll get is that is just straightforward algebra. Now, let us assume that what happens if I take these two equal, exactly equal. So that term will drop out. And so in that case, I write two energies as this should be a plus. Oh, okay. So I'm taking them to be equal. So this. So what does this mean? What it means is that again, it is best used in 1D. If I had such degenerate solutions, if this is equal to that, then we already argued that this can happen only at the Bragg planes. So if I have a Bragg plane in which the energy epsilon naught q and epsilon naught q minus g are exactly equal, then because of this periodic potential u, see, if u was zero, nothing would happen. The energies would remain the same. But if u is non-zero, this energy right at the Bragg plane would split up into two levels, one slightly above this, one slightly below this. So this is what the effect of u is in case of degeneracies. And I mean, this already gives you a lot of ideas or a lot of, this helps you to understand how the electronic structure, that is the band structure of systems which can be viewed within this framework, will look starting from the free electron picture. So we know how to deal with the free electron picture. All we need is the electron density, and then we can find out Fermi energy and Fermi velocity and so on and so forth. But when the electrons are actually experiencing periodic potential, things do change. But this framework, when applicable, gives us a way of starting from the free electron bands, free electron picture, and figuring out how the electronic energy levels change. And what we find here is that they change only near the Bragg planes. And if there is a twofold degeneracy, then they will be split into two levels right at the Bragg plane. And that splitting is twice the mod of UG there. So how does that help us to understand band structure of real solids, or for example, anything else that we can understand about real solids starting from a free electron picture? That is something we'll take up next time. Questions?
Sir, since the potential is weak compared to the energy levels, so can we use degenerate perturbation theory?
Well, this is like degenerate perturbation theory, right? So final expression that I wrote when there were in degenerate levels, I just wrote an equation within that subspace of degenerate levels. And
yes,
and so this determinant, for example, that I have written here, which gives me the energies of of the levels in presence of a finite U is basically that. I have kept terms only to leading order in U. What else? Everybody is rather quiet today. So have all of you submitted the second assignment? Is there anyone who hasn't?
Sir, I have not submitted. I will submit by evening.